Now, the next one is then the wired mesh networks, where we have not only point-to-point or point-to-point. Now we are becoming a little bit more networkish, right? It's not point-to-point, and therefore this recoding comes into the picture. I told you in the beginning, there are only two things that network coding can give you that makes network coding. The recoding and the latency. The latency, we looked into this. Now we would like to go into that, right? And if you think about mesh, there are so many things. We are talking about Internet of Things. You need to cluster them. Why? Because if you don't cluster them, then the energy consumption will be big if you always go to the base station. But if you think about cars talking to each other, you need a mesh over there. The drones flying in the air. Not everybody can talk to the base station, right? So there are different application fields there that you can see here. Of course, you will see here more throughput. You will even see resilience. I think we didn't even list it over here, but I think one example I brought you will tell you about the resilience. And then if you look for throughput, you have something here for delay, for energy consumption, and even quality of experience, which is, for example, resilience. And there's different implementation that we did at the chair, right, with Raspberry Pis and the dongles. People are running around. Krishna and his team, they made one implementation, what you can see here, in the old Barkhausenbau, and where you have a source and a destination here, and they have two repeaters / recoders, and then you have two routes to the destination, and they really implemented it. And what you see here is the first protocol they use is Batman, because one in the team, Simon Wunderlich, he's in the Batman team. Batman is a data link-based routing scheme, and he will say, okay, he will find out based on the number of hops and the link quality where to go. And as the number of hops is the same, it only depends on the better link, and Batman chooses the route A and comes up with a very low throughput, right? Very severe situation over there. Now, if you just say, instead of because Batman is using a repeater, instead of the repeater, let's use a recoder, then you could say, okay, what happened if I take the link that Batman didn't want to use because it's so bad? Now we are recoding at this point, and then you get a slightly higher throughput. If you take the same route as Batman, then you get a huge throughput. The nice thing is, if you combine them both at the same time, then you get even a higher one. So here, if you look at the numbers, this was 0.5, this is 0.58, so nearly 0.6 for the worst route, 1.5 for the better route, and if you take both, 1.89. You remember this duplicate thing that we talked about? Now it kicks in, right? So still, this is not the sum. If you sum this up, it's a little bit lower than that. The reason is, of course, the implementation is not fully tested, etc. pp, and they use the binary code. And if you hear binary, I want you to say 1.6, right? So then we have this example of the reliable multicast, and we already have this example in the cooperative wireless lecture, where you just feed in some streams into the stadium instead of giving everybody the one, and they should exchange it, right? And network coding can help to avoid duplicates for this guy over here. And then with the Raspberry Pis, in Aalborg we already started here, you see now Raspberry Pis with the same dongles. I think we have a huge amount of them, testing them out. Then the same what you have seen with 120, we started with the iPad, D2D, exchanging here something, also not only streaming it, but they could also help each other, right? We did the same with, this one is quite fixed. We can do this also with mobile equipment. I will not talk too much about this because this is also part in the cooperative wireless network class. But you can imagine when they start to move, it's more complicated. Because all the routing schemes, they assume, yeah, I can find out the situation. But if you cannot find out the situation, then it's very good to have the code. If you remember the storage, if you have the Genie implementation and you know what's going on, then you could prevent a little bit the damage to your data structure. But if you don't have it, then it collapsed, the ice cube collapsed right away. But with the network code, it was stable. And that is exactly what happens here. If they move too fast, okay. Now, the last thing that we did here is with the group Krishna and Simon Wunderlich and Frank Gabriel to really try to make this with drones. And I think last month they got granted an Exist funding package, so they can now start their own company, building up mesh networks based on this technology on drones. I will not make it a little bit less loud here. I don't know if you see. Not working. So this is the artificial game where you can go through a city. You are flying, and on the side you see where the drone is flying and how it connects to base station. This is a Meshmerize, which is a multi-link protocol, and you see the blue point is going very quickly, while the state-of-the-art is going, and every time you want to change the base station, it will stop, because it's only a single route, and when the single route has to refine a new base station, and this takes seconds. And this one is more resilient. And here you see the same in a real drone. The access points are on the ground, the drone is flying, and you have now 2 passes, now 3, 4, and you see where the throughput comes. In early days, this was a problem of duplicates and all. They can avoid this now and make it very resilient. So it's a very long way from the first idea to something like this.